Welcome to Dreamy Science, where we explore the fascinating world of scientific wonder. Here's a thought that might seem impossible to grasp, yet it sits at the very edge of our understanding. What if the universe, in its entirety, every star, every galaxy, every particle, and even the space and time that contain them, simply began from nothing? Not just an empty void, but the absolute irreducible absence of anything at all. When we talk about the Big Bang, we often picture an explosion, like a firework igniting in a vast pre-existing darkness. But that mental image is deeply misleading, because the Big Bang wasn't an explosion in space. It was the rapid expansion of space itself, bringing space and time and all the matter and energy within them into existence. So, if everything we know, literally everything, emerged from this singular, unimaginably dense, hot point, what was there before that point? If the Big Bang represents the beginning of space, time, and matter, then before doesn't even make sense in the way we usually understand it. It's a question that shatters our everyday intuition, forcing us to confront the limits of our language and our most fundamental concepts. It's a question that takes us beyond the observable universe, beyond the very fabric of reality as we perceive it, into a realm where, quote, when is far more complex and profound than simple emptiness. This isn't just a philosophical puzzle, it's a frontier of physics, where our best theories struggle to describe a reality utterly alien to our experience. If you're enjoying this journey through the fascinating world of science, I'd love it if you'd hit that like button and subscribe to Dreamy Science so you don't miss future episodes. And I'm always curious. Drop a comment letting me know what city you're watching from and what time it is where you are. There's something special about knowing this exploration of scientific wonder is reaching people all over the world at all hours of the day and night. Let's begin with a mind-bending idea that challenges our very definition of, quote, 2. When you imagine an empty void, you probably picture absolute blackness, stillness, a complete absence of anything. No particles, no light, no energy, not even space itself. But here's where physics gets genuinely strange. According to our most robust theories, such a nothing doesn't actually exist. Even the most perfect vacuum we could possibly create, stripped of every atom, every photon, every stray particle, is not truly empty. It's a seething, churning cauldron of activity, a vibrant ocean of potential. This isn't some philosophical musing, it's a fundamental prediction of quantum mechanics, a theory so successful it underpins nearly all modern technology, from lasers to microchips. So, if nothing isn't actually nothing, then the question of what existed before the Big Bang takes on an entirely new, even more fascinating dimension. To truly grapple with, quote, phi, we first need to understand what physicists mean when they talk about a quotest. In classical physics, a vacuum is indeed empty space, a region devoid of matter. Simple enough. But then quantum mechanics arrived in the early 20th century, and it shattered that elegant simplicity. Quantum mechanics tells us that everything, at its most fundamental level, behaves not just like a particle, but also like a wave. This wave-particle duality is crucial. It means that even fields, like the electromagnetic field that carries light, aren't perfectly smooth and continuous. Instead, they're subject to inherent, irreducible fluctuations. Think of it like this. If you could zoom in on the electromagnetic field, even in a region you thought was empty, you'd see tiny ripples, like the surface of a pond disturbed by an invisible breeze. These ripples represent fundamental uncertainties. This concept is formalized by Werner Heisenberg's uncertainty principle, one of the cornerstones of quantum mechanics. It states that you can't simultaneously know with perfect precision both the position and momentum of a particle, or, more relevant to our discussion, both the energy of a system and the time over which that energy is measured. There's an inherent fuzziness, a fundamental limit to what we can know about reality. The more precisely you know one quantity, the less precisely you can know the other. Now apply this to energy and time. The uncertainty principle implies that, for very short periods of time, the energy of a system can fluctuate wildly. This isn't just measurement error, it's a fundamental property of the universe. In an otherwise empty vacuum, energy can spontaneously appear and disappear, as long as it does so quickly enough to pay back its energy debt to the universe before it's caught. These fleeting bursts of energy are what we call, quote, qubits. They are not directly observable in the same way a real electron or photon is, but their effects are very real and measurable. Imagine a perfectly still, empty ocean. According to quantum mechanics, this ocean isn't still at all. It's constantly bubbling and churning with tiny waves and currents that spontaneously appear and vanish. These aren't real waves in the sense that they propagate across the entire ocean, but localized ephemeral disturbances. Similarly, virtual particles are pairs of particles and antiparticles, like an electron and a positron or a photon, that spontaneously pop into existence from the vacuum, exist for an incredibly brief moment, and then annihilate each other, returning their borrowed energy to the vacuum. This happens constantly, everywhere, all the time. It's the universe's most fundamental form of something for nothing, but only for a very, very short time. The implications of this not-so-empty vacuum are profound. It means that what we perceive as empty space is actually a dynamic, energetic medium. It's not a passive backdrop for cosmic events, but an active participant. This quantum vacuum energy has been experimentally confirmed through phenomena like the Casimir effect. In the 1940s, Dutch physicist Hendrik Casimir predicted that if you place two uncharged, perfectly parallel metal plates very close together in a vacuum, they would experience a tiny attractive force. Why? Because virtual particles with wavelengths larger than the gap between the plates are, quote, distance from appearing in that tiny space, while they can appear freely outside the plates. This creates an imbalance in the quantum fluctuations, pushing the plates together. This incredibly subtle force, predicted by the theory of virtual particles, has been measured with remarkable precision, confirming that the vacuum is indeed alive with quantum activity. So, if the vacuum is never truly empty, what does this tell us about the quote 13 before the Big Bang? It suggests that even before the universe as we know it began, there might have been a substrate, a primordial state of quantum potential. This isn't a state of absolute classical nothingness, but rather a quantum foam, a realm where space and time themselves become so intertwined and turbulent at unimaginably small scales that our familiar concepts of geometry and causality break down. These scales are known as the Planck scale, roughly 10^35 meters and 10^43 seconds. At this level, smaller than any particle we can ever hope to observe, the very fabric of space-time is thought to be undergoing constant, violent quantum fluctuations. It's not smooth and continuous, but rather a chaotic, probabilistic froth where tiny universes might be momentarily winking into and out of existence, only to collapse back into the foam. This idea of a quantum foam provides a compelling framework for thinking about the Big Bang's origin. Instead of a sudden burst from absolute nothingness, the universe could have emerged from a particularly energetic fluctuation within this pre-existing quantum foam. Think of it like a bubble forming in a boiling pot of water. The water is always there, always churning, and then from that underlying activity a bubble expands. In this analogy, the water is the quantum foam, and our universe is one such bubble, inflating rapidly and cooling to form the stars and galaxies we see today. This doesn't mean there was a, quote, 16 sin or for the foam to exist in, or a check 17 before the foam. Rather, the foam tinti is the most fundamental level of reality from which space and time, as we understand them, eventually emerged. It's a state where the laws of physics as we know them might not apply, where the very concepts of dimension and chronology are fluid and undefined. This perspective shifts our understanding from creation out of nothing to emergence from quantum potential. It doesn't answer why that particular fluctuation led to a universe, or if there are other, quote, 20 out there, but it provides a scientifically grounded alternative to absolute emptiness. It suggests that the Big Bang wasn't the first event in a linear timeline, but perhaps the point at which our specific space-time bubble began its expansion, a process that continues to this day. The universe, in a sense, didn't come from nothing, but from something incredibly subtle and profoundly quantum. It's a universe that always holds the potential for creation, even in its emptiest corners. So, we've begun to redefine nothing as a bustling, quantum mechanical sea of potential, a cosmic static before any signal. This underlying quantum activity, governed by the uncertainty principle, means that even the emptiest vacuum is teeming with virtual particles, constantly fluctuating in and out of existence. These tiny ephemeral events, however, don't just stay small. In the next chapter, we'll explore how these microscopic quantum fluctuations, if stretched to unimaginable scales during the very first moments of our universe's expansion, could have become the seeds for all the large-scale structures we observe today, the galaxies, the clusters, and the vast cosmic web. We'll delve into the theory of cosmic inflation, a period of exponential expansion so rapid it makes the Big Bang look like a gentle sigh, and discover how it bridges the gap between the quantum foam and the grandeur of the cosmos. Welcome back, truth seekers and cosmic adventurers, to dreamy science. Last time, we dove headfirst into the mind-bending reality that nothing isn't truly nothing at all. We peered into the seething, churning cauldron of the quantum foam, a realm where space-time itself is a probabilistic froth, and virtual particles flicker in and out of existence like cosmic fireflies. We learned that the Big Bang wasn't an explosion into empty space, but rather the energetic expansion of space from this dynamic quantum potential. But how, you might ask, did that chaotic microscopic fuzz of quantum fluctuations give rise to the majestic ordered universe we see today? How did those fleeting ripples in the primordial soup become the blueprints for galaxies, stars, and even us? Ah, dear friends, that's where one of the most brilliant and mind-bending theories of modern cosmology steps onto our stage. Cosmic inflation. Imagine, if you will, the universe just a tiny fraction of a second after its emergence from the quantum foam, a speck smaller than an atom, incredibly hot and dense. For a long time, cosmologists grappled with some perplexing puzzles about this infant universe. Why, for instance, is the universe so remarkably flat? Not flat like a pancake, but in the sense that its geometry is very close to Euclidean, meaning parallel lines remain parallel. And why is the cosmic microwave background radiation, the faint afterglow of the Big Bang, so incredibly uniform across the entire sky, even in regions that, according to standard Big Bang models, should never have had time to interact and equalize their temperatures? This is like finding two distant strangers who have never met wearing identical, custom-made sweaters. How could they possibly be so similar? These were profound questions, and the standard Big Bang model struggled to answer them. Then, in the early 1980s, a revolutionary idea emerged: cosmic inflation. We hypothesized that in the very first, almost unimaginably brief moments after the Big Bang, from about 10^36 to 10^32 seconds, the universe underwent an extraordinary exponential growth spurt. We're talking about an expansion so rapid, so immense, that it makes the Big Bang's subsequent expansion look like a leisurely stroll. During this inflationary epoch, the universe didn't just expand, it inflated, stretching by a factor of at least 10 plus 26, possibly much, much more. To put that into perspective, imagine taking something the size of a single proton and stretching it to be larger than our entire observable universe in less time than it takes to blink. It's an almost unfathomable burst of cosmic growth. What drove this incredible expansion? We believe it was powered by a hypothetical energy field, which we call the inflaton field. Think of it like a temporary repulsive gravity. In most cases, gravity pulls things together, but during inflation, this field temporarily created a negative pressure, pushing space-time apart at an incredible rate. It was like a universe-sized spring, coiled tight with immense potential energy, suddenly releasing that energy to propel an unimaginable expansion. As the inflaton field rolled down from a high-energy state to a lower one, it converted its potential energy into the hot, dense matter and radiation that would eventually fill our universe. When it reached its lowest energy state, inflation ended, and the universe transitioned into the more familiar, slower expansion we associate with the traditional Big Bang. Now, here's where the magic truly happens, connecting our quantum foam from Chapter 1 to the large-scale structures of the cosmos. Remember those tiny, fleeting quantum fluctuations, those inherent uncertainties and virtual particles constantly popping in and out of existence even in a vacuum. They were still there during inflation, of course, because quantum mechanics never takes a break. Critically, these fluctuations weren't just in empty space, they were in the inflaton field itself. And because the inflaton field was driving this incredible, exponential stretching of space-time, it also stretched these microscopic quantum jitters. Imagine painting a tiny, almost invisible ripple onto a balloon. Now, inflate that balloon to an enormous size. What happens to your tiny ripple? It gets stretched, magnified, and becomes a large, observable bump or depression on the surface. This is precisely what we believe happened in the early universe. The minuscule subatomic quantum fluctuations in the inflaton field, which would normally vanish almost instantly, were frozen and stretched across vast cosmic distances by the hyper-rapid expansion of inflation. These weren't just random ripples anymore. They became primordial density perturbations. They were tiny, infinitesimal variations in the density of matter and energy across the nascent universe. Some regions had slightly more matter, some slightly less. They were like the faint, almost imperceptible brushstrokes on a canvas that would eventually become a masterpiece. Without inflation, these quantum fluctuations would have remained microscopic and irrelevant to the large-scale structure of the universe. But inflation acted as a cosmic amplifier, taking something unimaginably small, something that arose from the fundamental uncertainty of quantum mechanics, and blowing it up to macroscopic, even cosmic scales. It's a breathtaking thought. The very fabric of our universe, the distribution of its galaxies and clusters, has its ultimate origin in the quantum fuzz that existed before anything we could recognize as stuff. So we have these tiny density perturbations, these slightly over-dense and under-dense regions, imprinted on the universe by inflation. What happens next? This is where the universe's greatest architect, gravity, takes over. Gravity, as we know, loves to pull things together. Denser regions have a stronger gravitational pull. So over billions of years, these slightly over-dense regions began to attract more and more surrounding matter. It was a cosmic snowball effect. A region with a little bit more matter gravitationally tugged on its neighbours, drawing them in, becoming even denser, which in turn increased its gravitational pull, attracting even more matter. Meanwhile, the slightly under-dense regions became emptier as matter migrated away towards the denser pockets. Think of it like drops of water on a slightly uneven surface. The water will naturally flow towards the lowest points, eventually forming puddles and streams, leaving the higher points dry. In our universe, matter flowed towards these gravitational... Quote 25. The initial overdensities seeded by inflation. Over vast cosmic timescales, these tiny, quantum-seeded density perturbations grew and grew. The slightly denser regions became the gravitational wells where the first stars would ignite, forming the first galaxies. These galaxies in turn clustered together, drawn by their mutual gravity, forming galaxy clusters and eventually the immense superclusters that define the large-scale structure of our universe. Vast cosmic webs of galaxies interspersed with enormous voids. Every galaxy, every star, every planet, and yes, even you and I, can trace our origins back to those infinitesimally small quantum fluctuations, stretched and amplified by inflation, then sculpted by gravity. This isn't just a beautiful story we've dreamed up either. We have compelling observational evidence that supports this incredible narrative. The most profound evidence comes from the cosmic microwave background, CMB, radiation. The CMB is often called the Quote 26 of the universe. It's the faint afterglow of the Big Bang, radiation that was emitted when the universe was only about 380,000 years old, cool enough for electrons and protons to combine and form neutral atoms. Before this point, the universe was an opaque plasma, like a thick fog. But once atoms formed, light could travel freely, and this ancient light is what we detect today as the CMB. When we observe the CMB, we find that it is incredibly uniform in temperature across the entire sky. This uniformity was one of the puzzles inflation was designed to solve, but crucially it's not perfectly uniform. There are tiny, minuscule temperature fluctuations, variations of only a few parts in 100,000. Some spots are ever so slightly warmer, others ever so slightly cooler. These tiny temperature differences in the CMB are the direct observational evidence of those primordial density perturbations. The slightly warmer spots correspond to regions that were slightly denser and thus slightly hotter in the early universe, where matter had already begun to clump together. The slightly cooler spots correspond to slightly less dense regions. These are the direct fingerprints of those quantum fluctuations, stretched by inflation, before gravity had time to significantly amplify them into the grand structures we see today. Satellites like COBE, WMAP, and Planck have meticulously mapped these fluctuations, providing stunning confirmation of this inflationary picture. So, when we look at the CMB, we are literally seeing the seeds of all cosmic structure, laid down by quantum mechanics and amplified by inflation. It's a profound connection between the unimaginably small and the unimaginably large. The very universe we inhabit, with all its breathtaking complexity and beauty, is, in a very real sense, a quantum phenomenon writ large. This journey from a quantum foam to a structured cosmos challenges our most basic intuitions about existence. It suggests that the nothing before the Big Bang was a vibrant, dynamic arena of potential, not empty stillness. And it reveals that our universe, far from being a random explosion, is a consequence of fundamental physical laws, where even the most minute quantum jitters play a starring role in shaping cosmic destiny. Next time on Dreamy Science, we'll push the boundaries of this concept even further. If our universe emerged from a quantum potential, could there be other universes? What does this mean for the very definition of a universe? Get ready to explore the mind-bending possibilities of the multiverse and the implications of an infinitely expanding quantum landscape. Until then, keep dreaming big and keep asking those beautiful, impossible questions. All right, dreamers of the cosmos, welcome back to Dreamy Science. Last time we peered into the earliest moments after the Big Bang, witnessing the cosmic inflation that smoothed out our universe and stretched microscopic quantum fluctuations into the seeds of galaxies. We saw how those tiny, probabilistic ripples in the quantum foam became the grand tapestry of stars and nebulae we observe today, imprinted on the cosmic microwave background. But we left you with a tantalizing thought, didn't we? A whisper of something even grander, something that challenges our very definition of reality. What if that incredibly powerful inflaton field, the engine of cosmic inflation, didn't just stop everywhere at once? What if it's still going somewhere out there? This, my friends, is where the concept of the multiverse truly begins to bloom. Imagine, if you will, a vast seething ocean of pure potential. The quantum foam we talked about, but now perpetually inflating. In some regions, like a bubble forming in boiling water, the inflaton field might decay, releasing its energy and creating a Big Bang event, just like the one that gave birth to our universe. But in other regions, the inflaton field keeps on inflating, relentlessly stretching space-time, creating more space for more bubbles to form. This idea is called eternal inflation. It suggests that inflation, once it starts, might never truly end across the entirety of this vast pre-existing quantum landscape. Instead, it generates a never-ending succession of bubble universes, each one budding off, expanding, and potentially evolving its own unique set of physical laws and constants. Think of it like this. You have a giant, ever-expanding balloon. Our universe is just one tiny inflated patch on that balloon. But imagine that balloon isn't smooth. It's constantly sprouting new, smaller balloons from its surface, which then inflate themselves, and they sprout even more balloons. Each of these bubble universes is an isolated pocket of space-time, an island in an infinitely larger cosmic sea. We can't see them, we can't touch them, and we can't directly communicate with them because the space between them is still inflating too rapidly for any signal to ever cross. So when we talk about the multiverse, we're not just talking about an infinite number of parallel universes existing in the same space. No, this isn't science fiction's typical mirror worlds. We're talking about a vast, perhaps infinite collection of genuinely separate universes, each born from its own Big Bang event within this larger, eternally inflating meta-universe. Each universe might have its own unique history, its own set of fundamental particles, its own gravitational constant, even its own speed of light. It's a dizzying thought, isn't it? Our entire observable cosmos, with its billions of galaxies, its unfathomable distances, its intricate laws of physics, all of it could be just one microscopic speck in an infinitely larger, endlessly bubbling cosmic brew. Now, you might be asking, quote 34, and that's a brilliant question. The concept of the multiverse isn't just a flight of fancy. It arises naturally from the very theories we use to explain our own universe, particularly cosmic inflation and quantum mechanics. One of the most compelling reasons for considering a multiverse comes from the incredible fine-tuning of our own universe. We've often marveled at how precisely balanced the fundamental constants of physics are. If gravity were slightly stronger, stars would burn out too quickly. If the electromagnetic force were slightly weaker, atoms wouldn't form stable molecules. If the initial conditions of the Big Bang were even infinitesimally different, we wouldn't have a universe capable of supporting life, or even complex structures like galaxies. It's almost as if our universe was designed for us. This leads us to the anthropic principle. Simply put, it suggests that the reason we observe the universe to have the properties it does is because if it were any different, we wouldn't be here to observe it. In the context of a multiverse, this principle takes on a powerful new dimension. If there are countless universes, each with different physical laws and constants, then it's not surprising that we find ourselves in one of the rare universes where conditions are just right for life to emerge. It's like winning the cosmic lottery. If you buy enough tickets, someone is bound to win the jackpot. In this case, we are the jackpot winners, residing in a universe perfectly tailored for our existence. This isn't to say the multiverse is a universally accepted theory. Far from it. It remains one of the most speculative and hotly debated ideas in modern cosmology. The biggest challenge, of course, is that we have no direct observational evidence of other universes. By their very nature, these, quote, 35 are beyond our cosmic horizon, forever out of reach. We can't point a telescope at another universe and say, there it is. However, the beauty of science is that even highly theoretical concepts can have testable implications, or at least provide elegant solutions to existing puzzles. For example, some theories suggest that if our universe collided with another bubble universe in its very early stages, it might leave an imprint, a subtle bruise or anomaly in the cosmic microwave background radiation. Scientists are actively searching for such patterns, though none have been definitively found yet. Another fascinating implication arises from the quantum nature of the multiverse. Remember how we said that even nothing is a seething quantum foam? Well, this applies to the creation of these universes too. The very act of a new universe budding off from the inflating background is fundamentally a quantum process, driven by quantum fluctuations in the inflaton field. So, in a profound sense, the multiverse itself is a manifestation of that same restless, probabilistic quantum potential that we explored in Chapter 1. It's the ultimate expression of the idea that from nothing, a dynamic, energetic vacuum, everything, and perhaps every possible thing can emerge. This picture of an eternally inflating multiverse, constantly spawning new realities, offers a truly mind-bending answer to our initial question. What existed before the Big Bang if there was nothing? It suggests that nothing was never truly empty. Instead, it was an incredibly fertile, dynamic substrate, a vibrant ocean of potential perpetually giving birth to new cosmic islands, each a universe unto itself. Our Big Bang wasn't the absolute beginning of everything, but rather a local event, a singular moment of creation within an infinitely larger, older and stranger reality. It's a humbling thought, isn't it? To realize that our entire universe, with all its grandeur and complexity, might just be one of an infinite number of cosmic experiments, each playing out its unique story. It expands our sense of wonder beyond anything we ever imagined, pushing the boundaries of what we consider possible. But if our universe is just one bubble, and if that larger inflating space is where new bubbles are constantly forming, what then lies beyond that? Is there an even grander framework? What is the ultimate source of this eternally inflating quantum realm? These are the questions that continue to drive us, the tantalizing mysteries that keep us gazing at the stars and delving deeper into the fabric of reality. Next time on Dreamy Science, we're going to push the boundaries even further. We'll explore theories that suggest space and time themselves aren't fundamental, but rather emergent properties. We'll dive into concepts like quantum gravity and string theory, trying to understand what might exist at the very, very deepest level of reality, before even the quantum foam. Get ready, because we're about to explore the true meaning of ultimate nothingness, or rather, the ultimate somethingness that underpins everything. You won't want to miss it. Welcome back to Sextist Quote, where we pull back the cosmic curtain and peer into the most mind-bending mysteries of existence. Last time, we dove headfirst into the exhilarating yet profoundly humbling concept of the multiverse, an infinite ocean of Magica, quote 45, constantly budding off from an eternally inflating quantum realm. We explored how this grand cosmic tapestry might address the perplexing fine-tuning of our own universe, suggesting that perhaps we simply exist in one of the countless bubbles where the conditions for life just happen to be right. But, as always, every answer in science seems to unveil a deeper, more tantalizing question, doesn't it? If our universe is just one bubble in an endless frothing cosmic champagne, then what, we ask you, is the ultimate source of that champagne? What underpins the eternally inflating quantum realm itself? What are the fundamental laws, the foundational fabric from which all these universes, all this potentiality springs forth? And perhaps most profoundly, What about the very stage upon which this cosmic drama unfolds, space and time themselves? Are they fundamental, or are they two mere illusions, emergent properties of something far more primal? Today, we journey beyond the known, beyond even the speculative, into the realm of theoretical physics' most audacious quests. The search for quantum gravity and the tantalizing promise of string theory. We're talking about the very bedrock of reality, the ideas that might finally unify the disparate languages of the cosmos. You see, for all our incredible progress, our understanding of the universe is still, in many ways, a symphony with two distinct, powerful, yet stubbornly unharmonious movements. On one hand, we have Albert Einstein's magnificent general relativity, the theory that describes gravity not as a force, but as the curvature of space-time itself, warped by mass and energy. This theory works beautifully on the grand cosmic scale, explaining the dance of galaxies, the expansion of the universe, and the enigmatic pull of black holes. On the other hand, we have quantum mechanics, the astonishingly successful framework that governs the microscopic world of particles and forces. It reveals a universe that is fundamentally probabilistic, where particles can be in multiple places at once, and where, quote 46, is a seething, churning cauldron of virtual particles popping into and out of existence. Quantum mechanics explains everything from the glow of a light bulb to the stability of atoms, but it typically operates on a flat, unchanging space-time background. The problem, my curious friends, arises when we try to bring these two titans together, where gravity becomes incredibly strong and space-time becomes incredibly tiny, like at the heart of a black hole, or the very first moment of the Big Bang. Both theories scream and break down. They give us nonsensical answers, infinite values, mathematical paradoxes. It's like trying to describe the same phenomenon using two completely different dictionaries that don't share any common words. We need a unified language, a theory of quantum gravity that can describe gravity in the quantum realm, that can tell us what space-time is at its most fundamental, granular level. This is where the true adventure begins, where we push past the limits of what we can directly observe and delve into the elegant, yet often mind-bending landscapes of theoretical physics. Imagine, if you will, that the fundamental building blocks of our universe aren't tiny, indivisible points, as we once believed. Instead, picture them as infinitesimally small, one-dimensional vibrating filaments, like minuscule cosmic rubber bands. This, my friends, is the core, breathtaking idea behind string theory. In this revolutionary view, every particle we know, electrons, quarks, photons, even the graviton, the hypothetical particle that mediates gravity, isn't a point, but a different vibrational mode of these fundamental strings. Just as a violin string can produce different musical notes depending on how it vibrates, a fundamental string can manifest as an electron if it vibrates one way, a photon if it vibrates another, and a graviton if it vibrates yet another. The entire universe then becomes a grand cosmic symphony, played out on these vibrating strings. The elegance of string theory is that it naturally incorporates gravity. One of the vibrational modes of these strings is the graviton, meaning gravity isn't an add-on, it's an intrinsic part of the theory. This is a monumental step towards quantum gravity, offering a potential bridge between general relativity and quantum mechanics. But, And here's where it gets truly wild. String theory comes with a catch, or rather, an expansion. For the mathematics to work out, for the theory to be consistent and avoid anomalies, these strings don't just exist in our familiar 4 dimensions of space-time, 3 spatial dimensions plus time. Oh no, string theory requires the existence of those extra dimensions, typically 10 or 11 dimensions in total. So, quote 47. You might be thinking, so quosus ant fortius di, and excellent question, and one that brings us to another fascinating concept: compactification. Imagine a garden hose pipe stretched across a vast field. From far away it looks like a one-dimensional line, but if you get closer, you realize it has a second dimension, its circumference, curled up so tightly that you can't perceive it from a distance. Similarly, string theory proposes that these extra dimensions are compactified, curled up into incredibly tiny, intricate shapes, far smaller than an atom, at every point in our familiar 4-dimensional space-time. These curled-up dimensions, though unseen, would influence the way strings vibrate, and thus determine the properties of the particles we observe. It's a bit like the hidden geometry of these extra dimensions dictating the very laws of physics we experience. Brains, the bulk, and the multiverse reimagined. As string theory evolved, it became clear that it wasn't just about one-dimensional strings. It suggested the existence of higher-dimensional objects called brains, short for membranes. These branes can be anything from 0-dimensional, a point, 1-dimensional, a string, 2-dimensional, a surface, up to even 9-dimensional objects, all existing within a larger, higher-dimensional space known as the bulk. And here, my friends, is where we begin to weave string theory back into our discussion of the multiverse and the ultimate origin. What if our entire universe isn't just a bubble, but a 3-dimensional membrane floating within this vast higher-dimensional bulk? In this captivating picture, the particles and forces we experience, like electromagnetism and the strong and weak nuclear forces, would be cis, quote 52, on our brain, much like flies stuck to flypaper. But gravity, mediated by those open-ended graviton strings, could potentially leak out into the higher dimensional bulk, explaining why gravity seems so much weaker than the other fundamental forces. This, quote 53, scenario opens up truly profound possibilities for the origin of our universe. Instead of a singularity, the Big Bang could be the result of a cosmic collision between 2 or more branes in the bulk. Imagine 2 vast invisible membranes drifting through this higher dimensional space until they finally meet and smack into each other. The incredible energy released from such a collision could manifest as the Big Bang, igniting the creation of a new universe on the branes. This is the essence of ekpyrotic, or cyclic universe diados, models which propose that our universe is just one in an endless series of Big Bangs and Big Crunches born from the collisions of branes. This offers a tantalizing answer to, quote 54, other branes drifting in the bulk. And the multiverse isn't just an infinite collection of bubbles, it's an infinite collection of brains, perhaps colliding, splitting, and interacting in a vast multi-dimensional cosmic ballet. The eternally inflating quantum realm could be interpreted as the dynamic, ever-changing environment of this higher dimensional bulk, constantly churning out new brains or causing existing ones to interact. Is space-time an illusion? The emergent universe. But let's go even deeper. If space-time is curved by gravity, and if it's quantized at the smallest scales, And if our universe is just a brain, then what is space-time fundamentally? Could it be that space and time, which feel so absolute and fundamental to our experience, are actually not fundamental at all? Could they be emergent properties? Think of it this way. Temperature isn't a fundamental particle. It emerges from the collective motion of countless atoms. Pressure emerges from the collisions of molecules. In a similar vein, some theories of quantum gravity propose that space-time itself emerges from a more fundamental, deeper structure. What could this deeper structure be? In loop quantum gravity, another contender for quantum gravity, space-time is thought to be woven from discrete quantized loops or atoms of space, forming a kind of quantum foam at the Planck scale, the smallest conceivable length. In string theory, space-time could emerge from the intricate interactions and entanglements of strings and brains in the bulk. It's like the pixels on a screen. Individually, they are discrete units, but together, they create the continuous image we perceive. This idea that space-time is emergent is profoundly challenging to our intuition. We perceive reality as happening in space and in time. But what if space and time are just convenient descriptions, macroscopic approximations of a more complex, non-spatial, non-temporal reality at the quantum level? What if the answer to quote 57, before the Big Bang, wasn't just an empty void, but a state where space and time as we know them simply hadn't emerged yet? A vibrant ocean of potential where the very fabric of reality was yet to coalesce into the dimensions we inhabit. The journey continues, so where does this leave us, dear viewers? We've journeyed from a quantum foam of virtual particles through the exponential growth of inflation and the endless possibilities of the multiverse. Now we stand at the precipice of even grander ideas, a universe woven from vibrating strings, existing as a brain in a higher dimensional bulk, where space and time themselves might be emergent phenomena. The nothing before the Big Bang, then, is transformed from an empty void into a vibrant, multidimensional quantum dance of potentiality. It's not a lack of anything, but a superabundance of everything in its most fundamental, unmanifested form. These are not easy concepts, we know, but they represent humanity's most ambitious attempts to understand reality at its deepest level. While direct experimental evidence for string theory or extra dimensions remains elusive, the elegance and mathematical consistency of these ideas continue to inspire physicists around the globe. They offer a coherent framework to unite gravity with quantum mechanics, to explain the origin of our universe, and to paint a truly awe-inspiring picture of what lies beyond our immediate perception. Join us next time on Dreamy Science, as we continue to push the boundaries, exploring how these profound scientific theories might even intersect with philosophy and our deepest intuitions about the very nature of existence. The quest for what existed before the Big Bang and what nothing truly means is far from over, and we're thrilled to have you along for the ride. Welcome back, cosmic explorers, to another mind-bending journey on Quote Jerkda 61. Last time, we peered into the intricate dance of string theory, the fascinating possibility of brain worlds, and the truly revolutionary idea that our very notions of space and time might not be the fundamental bedrock of reality we always assumed. We left you contemplating a universe where these familiar dimensions are not primary ingredients, but rather emergent properties, bubbling up from a deeper, non-spatial, non-temporal quantum foam. And that, my friends, is precisely where we pick up today. Because if space isn't a pre-existing stage and time isn't a relentless universal clock ticking away independently, then what is the ultimate fabric of existence? What is the true, quote, 62 from which everything arises? This is where theoretical physics truly becomes indistinguishable from profound philosophy, challenging our deepest intuitions about what it means to be. We've all grown up with the idea of space as this vast, empty expanse, a canvas upon which the universe paints its wonders, and time, it's that arrow, always moving forward, carrying us from past to future. But what if these are just illusions, albeit incredibly persistent and convincing ones, that emerge only at certain scales and under certain conditions? Think about it this way. When you look at a shimmering pool of water, you see a smooth, continuous surface. But zoom in, deep into the molecular level, and you find individual H2O molecules constantly jostling and interacting. The yin quote 63 and gi quote 64. You perceive aren't properties of a single molecule. They emerge from the collective behavior of countless molecules. Or consider temperature. A single atom doesn't have a temperature. Temperature is a statistical property that emerges from the average kinetic energy of a large collection of atoms. In a similar vein, many physicists believe that space and time themselves might be emergent phenomena, born from the collective behavior of something far more fundamental. The breakdown at the Planck scale, where space and time falter. To understand this, we need to revisit the Planck scale, that impossibly tiny realm where the laws of quantum mechanics and general relativity clash violently. We're talking about distances of 10 euro 35 meters, the Planck length, and durations of 10 euro 43 seconds, the Planck time. These aren't just small numbers. They represent the theoretical limits beyond which our current understanding of physics completely breaks down. At these scales, the very concept of a smooth, continuous space-time, as described by Einstein's general relativity, becomes utterly meaningless. Space isn't a smooth manifold. It's thought to become a seething, turbulent, and discontinuous mess. And time, well, time gets even stranger. In certain formulations of quantum gravity, particularly those attempting to describe the universe at its absolute beginning, time seems to simply disappear. This is often referred to as the problem of time. Imagine trying to measure time with a clock that itself is subject to such extreme quantum fluctuations that its ticks are completely unpredictable, or even cease to exist in any discernible order. It's like trying to measure the precise temperature of a single atom. The concept just doesn't apply. So if space and time aren't fundamental, what is? What takes their place in the deepest reality? Loop quantum gravity, quantizing the fabric of space. While string theory, which we discussed last time, posits fundamental vibrating strings in higher dimensions, another major contender in the quest for quantum gravity offers a different, yet equally profound perspective. Loop quantum gravity, or LQG. Where string theory suggests that matter and forces are made of strings, LQG focuses on space itself. It proposes that space is not continuous, but rather discrete, quantized. It's not an infinitely smooth canvas. It's woven from tiny, indivisible, quote, 60sec. Think of it like a digital image. What appears smooth from a distance is, upon closer inspection, made of individual pixels. LQG suggests that space is fundamentally pixelated. These, quote 67, of space are not just points, they are conceived as tiny loops or networks, interconnected in intricate ways. These are called spin networks. Imagine a vast three-dimensional tapestry, but instead of threads, it's woven from these fundamental loops of quantum space. The length, area, and volume of space aren't continuous values. They come in discrete quantized units, determined by the properties of these spin networks. When these spin networks evolve over time, they trace out what are called spin foams. And here's the truly mind-bending part. In LQG, time itself is not a separate entity that flows independently. Rather, time emerges from the evolution and rearrangement of these spin networks. The universe isn't in space and time. Space and time are the universe, or at least they are properties that emerge from its most fundamental quantum structure. So, the smooth, seemingly continuous space-time we experience is merely a macroscopic approximation, an averaged-out view of this fundamentally granular quantum reality. It's like how a smooth ocean surface is an average of countless individual water molecules and their chaotic movements. Information as the ultimate foundation. It from bit. If space and time are emergent, and even matter and energy are manifestations of deeper quantum fields or vibrating strings, then what truly underpins everything? Many physicists and philosophers are converging on a radical idea: information. This concept is famously encapsulated in the phrase "it from bit," coined by the brilliant physicist John Archibald Wheeler. He proposed that every physical it, every particle, every field, even space-time itself, derives its existence ultimately from intangible bits of information. What does this mean? It suggests that the most fundamental level of reality isn't composed of particles, fields, or even strings, but of abstract information encoded in some unknown way. Our universe, in this view, is like a cosmic computation, or a vast, intricate network of informational relationships. One of the most compelling pieces of evidence, or at least strong theoretical hints, for this just ye quote 727 idea comes from the holographic principle. This principle, inspired by the physics of black holes, suggests that the information content of a three-dimensional volume of space can be entirely encoded on a two-dimensional surface that bounds it. Think of a hologram. It's a 2D image that contains all the information needed to reconstruct a 3D object. The holographic principle posits that our entire 3D universe, with all its galaxies, stars, and us, might be a holographic projection emerging from information encoded on a distant, two-dimensional boundary. It's a bit like living inside a cosmic projection screen, where the c'est quotient is 73. We perceive is a vivid, immersive illusion. This isn't just a quirky idea. It arises from deep theoretical work in black hole thermodynamics, where it was found that the entropy, a measure of information, of a black hole is proportional not to its volume, but to the area of its event horizon. This implies that the information about everything that falls into a black hole isn't lost in its volume, but is somehow stored on its surface. Extending this to the entire universe leads to the holographic principle. If our universe is a hologram, then the before the Big Bang question takes on a whole new dimension. It's not about finding a place or a time, but about understanding the fundamental informational structure from which our holographic reality, including space and time, emerges. Rougias, the pre-geometric, pre-temporal reality, a network of potential. So, let's bring it all together. If space and time are emergent and information is fundamental, then the nothing before the Big Bang wasn't empty space or a moment in time. It was a pre-geometric, pre-temporal state of pure potential, an abstract realm of quantum information and relationships. Imagine it not as a void, but as an infinitely complex abstract mathematical structure, a vast network of interconnected bits of information. In this deeper reality, there are no fastas quote 77 in the way we understand them, no still on ticking by. Instead, there are only relationships, probabilities, and potential. The Big Bang, then, wasn't an explosion in space and time. It was the emergence of space and time themselves from this pre-geometric substrate. It was the moment when this abstract network of information began to coalesce, or unfold, into the dimensions and temporal flow that define our cosmos. It was the birth of the stage, not just the play upon it. This transforms our understanding of nothing from an absence into a vibrant, dynamic, and incredibly rich source of all existence. It's not a blank slate, but a seething ocean of quantum information where the very fabric of reality is being woven. The grand challenge, probing the unseen. Of course, these are incredibly profound and speculative ideas. How do we test them? How do we experimentally verify the existence of spin networks, or confirm that our universe is a hologram, or probe a reality where space and time don't even exist? This is the grand challenge of modern theoretical physics. We are pushing the boundaries of what is conceptually possible, using the most sophisticated mathematical tools we have. We look for subtle clues in the cosmic microwave background. We search for gravitational waves that might carry echoes of the very early universe, and we build ever more powerful particle accelerators to probe the fundamental nature of matter. But ultimately, the realm of pre-geometric, pre-temporal reality lies so far beyond our direct observational capabilities that for now, we must rely on the elegance and consistency of our mathematical models and the philosophical implications they carry. A universe of endless wonder, what we've explored over these chapters, from the quantum foam to the multiverse, from string theory to emergent space-time, paints a picture of a universe far more mysterious and magnificent than we could have ever imagined. The Yerstiu Quutquiu A2. Before the Big Bang is not a simple void, but a profound, active and fundamental layer of reality, brimming with potential. It challenges us to let go of our everyday intuitions and embrace a cosmos that operates on principles far stranger and more beautiful than we can easily grasp. It reminds us that our understanding is always evolving, always deepening, and it fills us with an exhilarating sense of wonder at the sheer ingenuity of the universe itself. So, as we bring this exploration to a close, we hope you feel not just informed, but inspired. Inspired to keep questioning, to keep exploring, and to marvel at the boundless mysteries that still await discovery. The universe, in its deepest essence, remains an enigma, a puzzle of unparalleled complexity and beauty. And we, here at Das System Quotia 83, are just scratching the surface. What are your thoughts on this mind-bending idea of emergent space and time? Does it resonate with you, or does it feel too abstract to be real? Share your questions and reflections in the comments below, because your curiosity is what fuels our journey. Join us next time on Quote 84. As we continue to push the boundaries of knowledge, perhaps venturing into the very nature of consciousness in a universe born from information. Until then, Keep dreaming, keep questioning, and keep looking up. All right, my curious cosmic explorers, welcome back to, quote, 85. We've embarked on quite the journey, haven't we? From the fiery birth of our universe to the baffling quantum foam, from the stretching fabric of inflation to the mind-bending concept of brains and the multiverse. We've peeled back layers of reality, challenging what we once thought was nothing, and finding instead a vibrant, seething ocean of potential. But in our last session, we touched upon perhaps the most profound, most revolutionary idea yet, the possibility that space and time themselves aren't fundamental, that they emerge from something even deeper, something pre-geometric, pre-temporal. We spoke of a realm where reality might be, just quote 87, where space is an intricate network of quantum loops and time is just the evolution of these connections. And at the very heart of this pre-existence, we posited a radical concept: information. Quote, "It is, as the brilliant physicist John Wheeler famously put it, what does that even mean? How can our vast, tangible, breathtaking universe, with all its galaxies, stars, planets, and even jewels, arise from mere information? That, my friends, is the grand mystery we're diving into today, plumbing the depths of reality's ultimate foundation. Get ready, because this is where physics truly starts to feel like poetry. When we talk about information as the fundamental building block, we're not talking about the kind of information stored on your smartphone or in a library book. We're talking about something far more abstract and intrinsic. Imagine the universe not as a collection of particles, but as a colossal, self-organizing computation. Every particle, every field, every interaction isn't just a physical event. It's a bit of information being processed, a state, evolving. Think of it this way. At the most fundamental level, before space and time even exist, there might only be potential. A vast, intricate web of possibilities, defined by relationships and distinctions. Each bit represents a choice, a distinction between two states. Yes or no, here or there, spin up or spin down. These aren't physical objects. They are the rules and relationships that define what can exist. It's like a cosmic blueprint, an incredibly complex data set that, when activated, renders our reality. So how do these abstract bits coalesce into the concrete reality we perceive? This is where the concept of emergence becomes absolutely crucial. We've seen emergence before, right? Water molecules are just H2O, but millions of them together emerge into the property of wetness. Individual neurons fire, but their collective activity emerges into consciousness. In the same vein, space, time, and matter might emerge from the collective behavior of these fundamental informational bits. Consider the idea of entanglement. We've talked about it before, how two particles can be linked, sharing a destiny no matter how far apart they are. What if this isn't just a quirk of quantum mechanics, but a fundamental linker of information? Imagine that the very fabric of space is woven from these entangled relationships. As these informational bits become entangled, they form connections, defining proximity and distance. These connections over vast scales could then give rise to the geometry we experience as space. Distance, then, wouldn't be a given. It would be an emergent property of how information is connected. And time, if space emerges from interconnected information, then time could be the process of these connections evolving, changing, and processing new information. It's not a river flowing by itself. but rather the unfolding sequence of informational states. Each, quote 91, is a new configuration of these fundamental bits. The Big Bang, then, wouldn't just be a singular explosion in pre-existing space and time, it would be the initialization of our universe's informational processing, the moment when this pre-geometric potential began to resolve into the specific, ordered reality we inhabit. This perspective radically transforms our understanding of the Big Bang. Instead of a cosmic firework igniting in a void, imagine it as a phase transition, much like water turning into ice or steam. In this informational paradigm, the quote 92 word before the Big Bang wasn't empty. It was a state of pure, undifferentiated quantum information, a seething, probabilistic froth of potential states. The Big Bang was the moment this undifferentiated information collapsed or resolved into a structured, expanding universe. It's the moment the cosmic computer, quote 93, selecting a specific configuration from an infinite array of possibilities, and those tiny quantum fluctuations we discussed, which inflation stretched into the seeds of galaxies. From this informational perspective, they weren't just energy fluctuations, they were informational perturbations in the primordial data set. Slight variations in the initial informational configuration, which then got amplified, eventually leading to the rich tapestry of cosmic structures we observe today. It's an elegant, if mind-bending way to unify the incredibly small with the incredibly large. Now, this leads us to some truly profound questions. If the universe is fundamentally information, does that imply a programmer? Or is it a self-organizing system where complexity simply emerges from simple rules? The beauty of this framework is that it doesn't necessarily require an external agent. The laws of physics themselves, in this view, could be the fundamental algorithms, the rules by which this cosmic information processes itself. Think about the multiverse again. If our universe is one specific informational configuration that emerged from the pre-geometric realm, then the multiverse could simply be the infinite array of other possible configurations that could have emerged, or are emerging, from that same fundamental informational potential. Each bubble universe, with its unique laws and constants, would be a different program running on the same underlying informational substrate. This offers a deeply compelling, albeit still speculative, explanation for why our universe seems so perfectly tuned for life. We simply find ourselves in one of the informational configurations where life is possible. Of course, directly observing. These fundamental bits of information, or the process of their emergence, is beyond our current technological capabilities. We're talking about scales far smaller than anything we can probe. The Planck length, the Planck time. But that doesn't mean we can't explore these ideas mathematically and through theoretical models. Scientists are actively working on theories of quantum gravity, like loop quantum gravity, which attempt to describe this granular informational nature of space-time. They're trying to build the mathematical bridges from the abstract realm of information to the concrete reality of our universe. This journey to understand Cotillon 97 has led us to a place where reality is more fluid, more dynamic, and more mysterious than we could have ever imagined. It transforms, quote 98, from an absence into a plenum, a fullness of pure potential, a vibrant ocean of quantum information, forever churning, forever capable of giving birth to new realities. What does this mean for our perception of reality? It suggests that our everyday experience of a solid, three-dimensional world moving forward through a linear time is an incredible emergent illusion, a highly convincing projection from a deeper, more abstract reality. It means that the universe isn't just out there. In a very real sense, it's being computed into existence, moment by moment, through the processing of fundamental information. It challenges our deepest intuitions. It asks us to consider that everything we perceive as real, every star, every atom, every thought, is ultimately a pattern of information. Does this diminish our existence? We at a quote 99 would argue precisely the opposite. It elevates it. It makes our universe a marvel of self-organization, a breathtaking dance of fundamental bits creating galaxies and consciousness. The quest to understand, quote $100, has evolved into a quest to understand the very nature of existence itself. We've moved from asking what was there to asking what is the fundamental fabric from which everything arises. And the answer, at the bleeding edge of theoretical physics, points towards a universe born not from a void, but from a vast pre-geometric, pre-temporal realm of pure quantum information. This isn't the end of the story, my friends. It's merely the beginning of a new chapter in human understanding. The questions we've explored today about information, emergence, and the true nature of reality are the questions that will drive physics for centuries to come. What deeper secrets lie hidden within the cosmic code? How will future observations and experiments allow us to glimpse this informational substrate? We stand at the threshold of a new era of discovery, where the boundaries between physics, philosophy, and even computer science begin to blur. The universe, in its ultimate essence, might be the most incredible, most complex, and most beautiful information system imaginable. And we, with our curious minds, are part of its ongoing computation, part of its emergent story. So, as we bring this exploration to a close, I invite you to carry these ideas with you. Look up at the night sky, or simply look around you, and ponder the incredible possibility that everything you see, everything you feel, everything you are, is an intricate, emergent pattern of fundamental information. It's a thought that humbles, inspires, and fills us with an unshakable sense of wonder. Thank you for joining us on this mind-bending journey through the cosmos and beyond, here on quote Life. Keep questioning, keep exploring, and keep dreaming of the incredible realities yet to be uncovered. Until next time, stay curious. Welcome back, Cosmic Explorers, to another mind-bending journey on our quote one. We left off on a truly profound precipice, didn't we? We had just begun to grapple with the idea that space and time, those seemingly immutable foundations of our reality, might not be fundamental at all. Instead, we proposed they are emergent properties, much like the wetness of water emerges from countless H2O molecules, or the intricate patterns on your screen emerge from lines of code. And at the very deepest level, we hinted at something even more astonishing. That information itself is the ultimate foundation of reality. It from bit, we called it, echoing the words of the brilliant physicist John Wheeler. Now, let's really dive into what quote unraveling means, because this isn't just a clever phrase, it's a paradigm shift that redefines everything we thought we knew about existence. If information is truly fundamental, then our universe isn't built from tiny solid particles in a void. It's built from relationships, from data, from quantum possibilities, that resolve into the structured reality we perceive. Think of it this way. What if the universe isn't a giant machine made of cogs and gears, but an incredibly complex self-organizing program? Imagine a computer game. You see characters, landscapes, intricate details, all rendered in stunning graphics. You can interact with them, feel immersed in their world. But beneath it all, what truly exists? Not physical mountains or rivers, but lines of code, algorithms, and data points. The entire experience, the entire world within the game, is an emergent phenomenon of that underlying information. In a similar vein, our dreamy science hypothesis suggests that our universe, with all its galaxies, stars, planets, and even us, is the manifestation of a staggeringly vast, interconnected network of quantum information. This isn't about classical bits, like the ones in your computer that are either 0 or 1. No, we're talking about quantum bits, or qubits. These aren't just 0 or 1, they can be 0, 1, or both at the same time through the magic of superposition. They can also be entangled, meaning their fates are inextricably linked, no matter how far apart they are. So imagine a reality where the fundamental building blocks are not tiny billiard balls, but these probabilistic interconnected quantum states. The universe, in this view, is a vibrant dynamic ocean of potential, a symphony of uncollapsed states waiting for resolution. So, what then was the Big Bang? If information is fundamental and space and time are emergent, then the Big Bang wasn't merely an explosion in space and time, it was the initialization of space and time themselves. It was the moment when this pre-geometric, pre-temporal realm of pure quantum potential underwent a profound phase transition, resolving into the structured informational universe we inhabit. Think of it like water boiling. Below 100 degrees Celsius, it's liquid water. Above 100 degrees, it's steam, a completely different phase with distinct properties, even though it's still H2O molecules. The Big Bang we propose was a cosmic phase transition on an unimaginable scale. Before this transition, there was no quote 106 to be, no quote 107 to experience. There was only a seething, churning cauldron of quantum information, a vast interconnected network of raw quantum data, a plenum of pure potential. This wasn't nothing in the sense of emptiness. It was nothing in the sense of undifferentiated potential. Everything and nothing all at once. A realm where probabilities danced without ever settling into definite realities. Imagine a canvas before the artist begins to paint. It holds the potential for any masterpiece, any landscape, any portrait. It's not empty, it's full of possibilities. The Big Bang, then, was the moment the cosmic artist began to paint, choosing a particular set of strokes, a particular palette, from the infinite possibilities available. It was the moment the universe booted up, transitioning from a state of pure, unmanifested quantum information into the specific, structured information that defines our cosmos. This initialization wasn't a sudden burst from absolute silence into deafening noise. Instead, it was the unfolding of information, the resolution of quantum potential into the classical reality we observe. The quantum foam we discussed earlier, that chaotic, probabilistic froth of virtual particles constantly popping in and out of existence, can be seen as the physical manifestation of this underlying informational plenum. The Big Bang, in this light, was the moment this foam, this potential, cohered and expanded into the structured fabric of space-time and matter. But what triggered this initialization? What caused this phase transition? This is where the mystery deepens even further, isn't it? In quantum mechanics, potential states resolve into definite realities through measurement or observation. So if the universe itself underwent this resolution, who or what was the observer? This question leads us to the very edge of physics and into the realm of profound philosophical inquiry. Some physicists suggest the universe might be observing itself, that the very interactions within the nascent cosmos acted as the measurements that collapsed the wave function of pure potential into the reality we know. It's a breathtaking thought. The universe, in its infancy, coming into being by observing itself. From this perspective, the quote 1:14 before the Big Bang wasn't an empty void, but a plenum of pure quantum information, an infinitely rich tapestry of potential that simply hadn't resolved into specific forms, hadn't yet rendered space, time, or matter. It was the ultimate source code, pregnant with all possible universes, waiting for the cosmic run command. Our universe, with its specific laws and constants, is just one particular output from that vast informational wellspring. This redefinition of reality challenges our fundamental intuitions. We are so accustomed to thinking of reality as something solid, tangible, existing out there independently of us. But if space, time, and matter are all emergent from information, then our perceived reality is, in a very deep sense, an illusion. Not in the sense that it's fake, but in the sense that it's a highly sophisticated interface to a deeper, more abstract informational substrate. Just as the vivid world of a dream feels utterly real while you're in it, even though it's an emergent experience of your brain, our universe might be the emergent experience of a vast, interconnected quantum information network. This journey, from a dynamic quantum foam to an information-rich plenum, has completely transformed our understanding of nothing. It's not an absence, it's a presence of infinite potential. It's not empty, it's full of the raw ingredients of existence. And the Big Bang, rather than being a mysterious explosion from an unknowable void, becomes the grand initialization event, the moment the universe's cosmic program began to run, giving rise to space, time, and all the wonders within. So, what does this mean for our place in this grand informational cosmos? What does it imply about the nature of consciousness if reality itself is fundamentally informational? These are the kind of questions that continue to drive us here at quote Walate, pushing the boundaries of human understanding. Join us next time as we delve into the implications of this informational universe and explore even more radical ideas about what might lie beyond the edges of our current understanding. The journey, dear friends, has only just begun. So, we've journeyed through the quantum foam, surfed the waves of inflation, peeked into the multiverse, and even imagined our universe as a grand cosmic computation emerging from a plenum of pure potential. We've redefined just of quote Feynman de Osnewasan into scan kyo. Zastem tuus twistu best, transforming an empty void into a vibrant ocean of possibility. But here's the kicker, the question that keeps every physicist and cosmologist up at night. How do we know any of this is true? You see, for all the breathtaking elegance and profound explanatory power of theories like string theory, loop quantum gravity, and these CERN quote 123, hypothesis, direct observational evidence remains maddeningly elusive. We've built these magnificent conceptual cathedrals stretching the very limits of human imagination, but the cosmic architects are still searching for the foundational bedrock of empirical proof. This isn't a weakness, it's the very nature of cutting-edge science. We formulate hypotheses, we build models, and then we devise ingenious ways to test them, pushing the boundaries of technology and observation. So, where do we look for confirmation of a universe that emerged from pure information, or a Big Bang that was merely an initialization from a pre-geometric realm? Let's dive into the cosmic detective work. The cosmic microwave background, our faintest whisper from the dawn of time. Remember the cosmic microwave background, CMB? That faint ancient afterglow of the Big Bang, a snapshot of the universe when it was just 380,000 years old. We've often called it the baby picture of the universe. But it's more than just a picture. It's a canvas holding the subtle brushstrokes of primordial events, a canvas we're only just beginning to truly decipher. The tiny temperature fluctuations in the CMB provide compelling evidence for cosmic inflation. But future, more sensitive CMB experiments are designed to hunt for even more subtle clues. We're talking about detecting primordial gravitational waves. These would be ripples in space-time generated during the inflationary epoch itself, leaving a unique polarization pattern in the CMB known as B modes. Finding these would be like hearing the very first rumble of the universe's birth, a direct confirmation of inflation, and a potential window into the energy scales where quantum gravity effects might have been dominant. Imagine that. A signal from a time when the universe was less than a trillionth of a trillionth of a trillionth of a second old. Beyond B modes, cosmologists are also scrutinizing the non-Gaussianities in the CMB. Gaussianity refers to the statistical distribution of these temperature fluctuations. If inflation was a simple, single field process, we expect these fluctuations to be very Gaussian. However, if there were more complex dynamics, or if our universe is just one bubble in a vast multiverse, these non-Gaussianities could reveal themselves as subtle deviations from a perfect bell curve. This could be our first observational hint of other universes, a whisper across the cosmic foam, suggesting that our bubble isn't alone. Gravitational waves, listening to the universe's deepest resonances. Our new era of gravitational wave astronomy, pioneered by detectors like LIGO and Virgo, has opened an entirely new sensory input for understanding the cosmos. So far, we've mostly detected mergers of black holes and neutron stars, violent, cataclysmic events in their present universe. But the true holy grail for our quest lies in detecting primordial gravitational waves that originated from the very earliest moments of existence. Imagine a network of detectors, perhaps space-based like the proposed LISA mission, sensitive enough to pick up the faint, continuous hum of gravitational waves from the Big Bang itself. These wouldn't be sudden chirps from merging behemoths, but a steady background roar, a cosmic symphony composed at the quantum realm. Such a signal could carry information about the phase transitions of the early universe, the physics of inflation, and crucially, the nature of space-time at energies far beyond anything we could ever hope to recreate in a lab. It could even provide unique signatures for certain quantum gravity theories, like the predictions of string theory or loop quantum gravity, offering a direct probe of the pre-geometric information-based reality. We're not just looking for evidence, we're trying to listen to the very fabric of existence. Particle accelerators smashing our way to fundamental truths, while the cosmos provides us with ancient light and gravitational ripples. Particle accelerators like the Large Hadron Collider, LHC, offer a complementary approach, recreating the extreme conditions of the early universe in miniature. We can't directly smash strings together or observe extra dimensions with a microscope. But what we can do is search for subtle effects or new particles that are predicted by these advanced theories. For instance, if extra dimensions exist, they might manifest as new, heavier particles that decay in unusual ways, or even as tiny micro-black holes that briefly form and evaporate. Supersymmetry, a key component of many string theory models, predicts a partner particle for every known fundamental particle. Finding even one of these superpartners would be a monumental step towards validating the theoretical framework that underpins string theory. While the LHC has yet to reveal such definitive evidence, the next generation of accelerators, pushing to even higher energies, might just crack open these deeper layers of reality. We're essentially trying to find the pixels of information that make up our reality by recreating the moments when they were being rendered. The enigma of the trigger. What initiated the initialization? Even if we find compelling evidence for inflation, multiverses, or quantum gravity, a profound mystery still lingers. What caused the Big Bang to initialize? If our universe emerged from a plenum of pure potential, a realm of pure quantum information, what sparked its transition into the structured space-time-bound reality we inhabit? What was the trigger for this grand cosmic computation to begin running? This is where the concepts become even more mind-bending, pushing beyond what we can currently test into the very nature of existence itself. One fascinating idea comes from the no-boundary proposal by Stephen Hawking and James Hartle. It suggests that, in a quantum gravitational sense, the universe didn't have a singular beginning in time. Instead, it emerged from a state where space and time were so fundamentally intertwined and quantum that the very question of, quote 134, becomes meaningless. It's like asking what's north of the North Pole. The concept simply doesn't apply. The universe, in this view, simply is, emerging from a quantum state without a classical edge or boundary, a self-contained informational system that bootstrapped itself into being. Another perspective delves into the very concept of self-organization. If the universe is fundamentally information, a vast, self-organizing quantum computation, perhaps its initialization isn't an external event but an intrinsic property. Complex systems, from snowflakes to ant colonies, spontaneously generate intricate structures from simple rules. Could the universe, as a system of quantum information, possess an inherent drive towards actualization, towards resolving its vast potential into concrete reality? Perhaps the Big Bang was less of an explosion and more of a phase transition, like water freezing into ice, driven by the internal dynamics of the informational plenum. The potential was so vast, so rich, that its actualization was, in a sense, inevitable. And then there's the truly provocative notion that connects back to the very act of observation. If E from bit suggests reality emerges from information, and quantum mechanics tells us that observation plays a role in actualizing quantum possibilities, could the universe itself be, in some sense, observing itself into existence? This isn't to say that human consciousness created the universe, but rather that fundamental quantum processes of entanglement and decoherence, the very, quote, Jas 137, and Gahiosthian of information are what actualize potential into reality. Perhaps the conditions for observers had to arise because the universe needed to, quote, 139, its quantum state. It's a profound feedback loop where the universe creates observers, and observers, through their very existence, contribute to the universe's actualization. Some theories also propose that our Big Bang wasn't a unique singular event, but rather part of an eternal cycle. In these, as quote Chakanahunjahan 40 or cyclic models, the universe undergoes endless cycles of expansion and contraction, or perhaps our three-brain collides with another, triggering a new Big Bang. In this framework, the quote 141 Arian for our universe is simply the end of a previous one, pushing the ultimate quote question back, but offering a continuous self-sustaining process. The plenum of potential in this view is never truly dormant. It's constantly recycling, reinitializing, and reinventing itself. The enduring quest, why asking matters. Ultimately, dear dreamy scientists, the Kant quote 143 journey is about more than just finding definitive answers. It's about the profound act of asking the questions. It's about challenging our deepest intuitions, stretching our minds to encompass concepts that seem utterly alien, and embracing the humbling, yet exhilarating reality that we are still very much at the beginning of understanding our universe. The search for direct evidence for these advanced theories will continue to drive astronomical observation, particle physics experiments, and theoretical breakthroughs for decades, perhaps centuries to come. We will build more powerful telescopes, more sensitive detectors, and more sophisticated computational models. We will continue to chip away at the edges of the unknown, guided by the light of reason and the fire of curiosity. What existed before the Big Bang if there was nothing? We found that nothing was a vibrant, seething, information-rich plenum of pure potential. The Big Bang wasn't an explosion in space and time, but the very initialization of space and time, the glorious moment when possibility resolved into reality. And the quote wonderful pifav. Perhaps it was the universe itself, an inherent property of information-seeking actualization, a cosmic self-observation, or simply another turn in an eternal cosmic dance. The journey continues, and we, the collective, quote 146 are thrilled to have you along for the ride. Keep wondering, keep questioning, and keep dreaming, because the universe, in all its informational glory, is just waiting for us to ask the next big question. Welcome back, cosmic explorers, to us just, quote, 147. We've embarked on quite the journey, haven't we? From the bustling quantum foam of nothing to the elegant dance of string theory's brains and the pixelated reality of loop quantum gravity, we've peeled back layer after astonishing layer. We've come to understand that space and time themselves aren't fundamental, but emergent properties of a deeper, pre-geometric reality, a vibrant ocean of pure quantum information. The Big Bang, we've theorized, was less of an explosion and more of a phase transition, an initialization event where this undifferentiated potential resolved into the structured cosmos we inhabit. But, as always, Scientific discovery isn't about finding a final answer, it's about uncovering better questions. And having illuminated this incredible informational plenum, we're left with one of the most profound inquiries of all. What triggered that phase transition? What initiated the initialization? If the universe emerged from this cosmic computation, what started the program? This, dear friends, is the ultimate giant quote, 49. Behind the quote 150 gallon, the riddle of the Big Bang's first moment, if such a concept even applies when time itself was just beginning to unfurl. The spark of existence, theories of the trigger. Think of it this way. We've described the canvas and the paints, but what made the artist pick up the brush? What caused the quantum information to resolve into our universe, rather than remaining in its undifferentiated state? The truth is, we don't have a definitive answer, but we have some absolutely mind-bending theoretical proposals, each challenging our very intuition about beginnings. One of the most elegant, if counterintuitive, ideas is the no boundary proposal, famously put forth by Stephen Hawking and James Hartle. Imagine trying to find the beginning of the Earth's surface. You can travel north, but there's no quote 152 where the surface simply stops. It curves back on itself. The no-boundary proposal suggests that the universe's space-time might be similar. In this model, the universe didn't start at a singular point in time with a specific, identifiable boundary. Instead, it emerged from a state where the concept of time itself was initially fuzzy, becoming more well-defined as the universe expanded. It's like a path that has no beginning point, only a continuous flow. In this scenario, there's no, just a quote, 153 because time itself begins with the universe, and the universe essentially, quote 154, from nothing, without needing an external cause or a specific trigger event. It simply is, in a way that's mathematically consistent. It's a universe that self-organizes its own origin. Taking a slightly different philosophical tack, some theories flirt with the idea of Gabge, cosmic self-observation. We know from quantum mechanics that observation plays a crucial role in collapsing a wave function, forcing a probabilistic quantum state into a definite reality. Could the universe itself have observed itself into existence? This is a highly speculative concept, but it suggests that perhaps the very act of consciousness, or the potential for it, is intertwined with the universe's emergence. It's a deeply philosophical notion, hinting that the universe needed to become conscious, or at least potentially conscious, to solidify its own reality from the quantum froth. While captivating, it's also incredibly difficult to test empirically, pushing the boundaries of what we traditionally consider science. Then there's the compelling possibility of cyclic universes, or the Big Bounce scenario. What if our Big Bang wasn't the beginning, but merely a transition from a previous cosmic era? Imagine the universe as a cosmic accordion, expanding and contracting, breathing in and out. In this model, our universe reaches a maximum expansion, then begins to contract, eventually crunching down to an incredibly dense state. Not a singularity, but a quantum state of extreme density, before bouncing back into a new expansion, forming a new universe. This avoids the singularity problem entirely and offers an elegant solution to the what came before question. Another universe did. How might this bounce occur? String theory offers a fascinating mechanism. The collision of brains. Remember our three-brain universe floating in a higher dimensional bulk? What if the Big Bang was the moment our brain collided with another parallel brain? This collision would unleash immense energy, manifesting as the Big Bang and initiating our universe's expansion. In some brain cosmology models, these collisions could be a recurring phenomenon, leading to an endless cycle of Big Bangs and Big Crunches, or perhaps even Big Rips, as brains repeatedly interact. Similarly, loop quantum gravity, LQG, also offers a, quote, 61 as an alternative to the Big Bang singularity. In LQG, space-time is quantized, meaning there's a minimum possible size. This prevents gravity from collapsing matter into an infinitely dense singularity. Instead, when a collapsing universe reaches this minimum quantum volume, the repulsive forces of quantum gravity become dominant, causing it to rebound and begin a new expansion. The Big Bang, in this view, is simply the moment of maximum compression and subsequent rebound, a cosmic reset button. These theories, the no-boundary proposal, self-organization, and cyclic universes, each offer a unique perspective on the Big Bang's origin, moving us away from a singular, unexplained, just quote 161, gone event, towards a more intrinsic, self-consistent emergence. But how do we move from elegant theory to empirical evidence? The cosmic detective work. Hunting for clues. This is where the real fun begins, where Quotatus 162 meets the cutting edge of observation and experimentation. While we can't rewind time to witness the Big Bang, we can look for its faint echoes, its primordial fingerprints left behind in the fabric of space-time. Our primary tool in this cosmic detective work remains the Cosmic Microwave Background, CMB. This ancient light, the afterglow of the Big Bang, holds a wealth of information about the early universe. We've already discussed how the tiny temperature fluctuations in the CMB are the seeds of all structure in the universe, stretched out by cosmic inflation, but the CMB might hold even deeper secrets. Scientists are intensely searching for B-mode polarization. In the CMB, what's that, you ask? Think of light as a wave, oscillating in different directions. When light interacts with matter, its oscillation can become polarized, meaning it prefers a certain direction. The CMB light, when it was last scattered by matter in the early universe, acquired a specific type of polarization called E-mode. However, if there were primordial gravitational waves, ripples in space-time itself, crisscrossing the universe during the epoch of inflation, they would have also imprinted a unique, swirling pattern of polarization on the CMB light, known as B-mode. Detecting these B-modes would be nothing short of revolutionary. It would be direct evidence of inflation, confirming the existence of gravitational waves from the very early universe and offering a window into the energy scales and physics operating during that fleeting first fraction of a second. It would be a profound validation of our understanding of cosmic origins. Beyond B-modes, researchers are also scrutinizing the CMB for desi non-Gaussianities. The standard inflationary model predicts that the primordial fluctuations in the CMB should follow a very specific statistical distribution, known as a Gaussian distribution. However, if inflation wasn't perfectly smooth, or if our universe is just one bubble in a vast multiverse, these deviations could leave subtle, non-Gaussian signatures in the CMB data. Imagine a perfectly smooth pond, and then a tiny ripple appears. If that ripple expands to become an ocean, The overall pattern might still look smooth, but a slight asymmetry or clumpiness could reveal a deeper, more complex origin, perhaps even hints of collisions with other bubble universes. But the CMB isn't our only window. We're also entering the era of gravitational wave astronomy. Just as we search for primordial gravitational waves in the CMB, we are now building instruments capable of directly detecting gravitational waves passing through Earth. Detectors like LIGO and Virgo have already opened a new sense for observing the universe, picking up the powerful ripples from colliding black holes and neutron stars. But these are relatively recent violent events. What if we could detect the continuous hum of gravitational waves from the Big Bang itself, or from exotic phenomena in the very early universe? Future gravitational wave observatories, like the planned space-based Laser Interferometer, Space Antenna, LISA, or ground-based Pulsar Timing Arrays, PTAs, are designed to detect much lower frequency gravitational waves, which could carry information from much earlier cosmic epochs. Imagine listening to the ancient echoes of the universe's birth, a symphony of space-time reverberations that tell the story of its earliest moments. Such a detection would provide an unparalleled insight into the physics of the Big Bang, offering empirical constraints on theories like the Big Bounce or brane collisions. And let's not forget our tireless explorers on Earth, the particle accelerators. Facilities like the Large Hadron Collider, LHC, are not just smashing particles to discover new fundamental building blocks, they are also probing the very fabric of reality at incredibly high energies. Energies that existed in the universe only moments after the Big Bang. By recreating these extreme conditions, we hope to find evidence for new particles predicted by theories like string theory or supersymmetry, or even subtle signatures of extra dimensions. Imagine a tiny ripple in our 3D space, indicating a connection to a higher dimension, a whisper from the Spiegelheinstitriesti that our brain might inhabit. Future, even more powerful colliders could potentially push us closer to the energy scales where quantum gravity effects become dominant, offering direct experimental verification of theories that currently exist only on paper. The unending pursuit of understanding, so, where does this leave us? We are on the precipice of discovery, armed with increasingly sophisticated tools and brilliant minds. The journey to understand, quote-forwand, has transformed our concept of quote-fave into a dynamic, information-rich plenum. We are searching for the trigger, the spark, the initial conditions that brought our universe into being from this cosmic potential. But even if we find definitive evidence for inflation, for primordial gravitational waves, for a big bounce, or for extra dimensions, will we have truly answered the ultimate question? Will we ever fully grasp why there is something rather than nothing? Why do these laws of physics exist? Why did the informational plenum resolve in this particular way? These are questions that perhaps transcend science, delving into philosophy and metaphysics. Yet that doesn't diminish the incredible power of our scientific quest. Each layer we peel back reveals a universe more intricate, more beautiful, and more awe-inspiring than we could have ever imagined. We are on a journey of continuous revelation, pushing the boundaries of human knowledge, driven by an insatiable curiosity about our origins. Join us next time on Dreamy Science as we delve deeper into the philosophical implications of these discoveries, exploring the profound impact they have on our understanding of consciousness, reality, and our place in the cosmos. The universe, my friends, is still telling its story, and we are privileged to be listening. Welcome back to Dreamy Science, my friends, my fellow cosmic adventurers. We've journeyed through quantum foam, danced with inflation, peeked into the multiverse, and contemplated a universe woven from pure information. We've even dared to ask, what triggered it all? And we touched upon the incredible, painstaking quest for empirical evidence, the cosmic fingerprints left by the earliest moments of existence. Now, as we stand on the precipice of Chapter 10, we want to delve deeper into this quest. We've talked about the what and the how of testing these theories, the hunt for primordial gravitational waves in the cosmic microwave background, CMB, the whispers of non-Gaussianities hinting at other universes, the high-energy probes of particle accelerators searching for new dimensions or supersymmetric partners. But today, we want to talk about the why of this monumental effort, the challenges it presents, and the profound implications if we ever succeed in lifting the veil on the ultimate beginning. You see, finding this evidence isn't like stumbling upon a treasure chest. It's more like trying to discern the faint original brushstrokes on a masterpiece that has been repainted countless times over billions of years, then viewed through a swirling cosmic fog. The signals we're looking for, the B-mode polarization patterns in the CMB, for instance, are incredibly subtle. They are the faintest ripples from an event of unimaginable power, stretched and diluted across an expanding cosmos, and then potentially obscured by foreground emissions from our own galaxy. It's like trying to hear the single, opening note of a symphony played at the dawn of time, when that note has travelled across an entire universe, and now it's buried under the roar of galactic wind and the static of cosmic interference. Our instruments are marvels of engineering, yes, but they are still pushing the absolute limits of sensitivity. We are building telescopes that are effectively time machines, peering billions of years into the past, trying to catch the most ephemeral echoes of creation itself. This is why the scientific journey is rarely a sudden aha moment. It's a grueling collaborative marathon. It's about designing increasingly sensitive detectors, developing sophisticated algorithms to filter out the noise, and painstakingly collecting data over years, sometimes decades. Every tiny anomaly, every unexpected blip could be a false alarm, or it could be the first tantalizing hint of a revolutionary discovery. We don't just find the answer, we build it, piece by agonizing, exhilarating piece, through observation, hypothesis, and relentless testing. And this process isn't just about confirming existing theories. Sometimes the most exciting discoveries are the ones that force us to rethink everything. What if we detect something entirely unexpected? What if the data contradicts our most cherished models? That's when science truly thrives, when paradigms shift, and our understanding of reality undergoes a profound transformation. It's a testament to the scientific method, where even our grandest ideas must ultimately bow to the verdict of the universe itself. But what if these theories, these incredible leaps of imagination, prove to be correct? What if we do find definitive evidence that our universe is a bubble in a multiverse, or that space and time are emergent properties arising from a deeper pre-geometric reality? The implications, my friends, extend far beyond the realm of theoretical physics. They touch upon the very core of our existence, our perception of reality, and our place within the cosmos. Imagine, if you will, the profound shift in perspective if we truly internalize the idea that space and time are not fundamental. We live, breathe, and experience everything within the framework of space and time. Our very consciousness is rooted in a sequential flow of moments and a spatial extension. If these are merely emergent, like the ripples on a pond's surface arising from a deeper, unseen current, then what does that make us? Are we characters in a cosmic video game, existing within the rules of a simulated reality, unaware of the underlying code and hardware that generate our world? This notion challenges our most fundamental intuitions. It suggests that our common sense understanding of reality is just one layer, one specific resolution of a much richer, more abstract tapestry. What would it mean for causality if time itself is not absolute? What would it mean for free will if our universe is a vast, self-organizing quantum computation, where events unfold not in a linear progression, but through the resolution of entangled informational states? And this brings us back to that mind-bending idea of cosmic self-observation. If the universe is a plenum of pure quantum information, and if reality emerges from the collapse of possibilities into definite states, could the universe have, in some profound sense, observed itself into existence? Not with eyes, of course, but through an intrinsic informational feedback loop, a process where the very act of existing defined its own parameters. This isn't about a conscious entity watching the universe unfold in a traditional sense. It's about the universe as an informational system, a colossal quantum computer, where the processing of information itself leads to the emergence of structure, of space, of time, and ultimately of us. In this view, our own consciousness, our ability to observe and interpret, might not be an accidental byproduct, but rather an integral part of the universe's ongoing self-definition, its way of, quote, 1-20%. It's a truly humbling thought, isn't it, that we, these tiny collections of stardust, might be part of the universe's grand unfolding narrative, its way of bringing awareness to its own existence. It transforms our understanding of, quote, 172. From an empty void into a vibrant, information-rich plenum of potential, constantly processing, constantly evolving, constantly creating. Of course, these are incredibly speculative frontiers. We are venturing into territory where physics, philosophy, and even metaphysics begin to intertwine. They quote the four, why there is anything at all rather than absolute featureless nothingness, even the quantum foam kind, remains a question that may forever lie beyond the grasp of empirical science. But that doesn't diminish the wonder, does it? It only deepens our appreciation for the sheer mystery and elegance of existence. So, where do we go from here, as dreamy science continues its journey? The quest for understanding the universe's origins is far from over. We are on the cusp of a new era of discovery. Future generations of observatories, like the James Webb Space Telescope, already showing us the earliest galaxies, and proposed gravitational wave detectors in space like LISA, Laser Interferometer Space Antenna, promise to open new windows onto the cosmos. More powerful particle colliders are still on the drawing board, designed to probe energies closer to the Big Bang itself, searching for the elusive particles and forces that shaped our reality. The convergence of different theoretical frameworks, string theory, loop quantum gravity, theories of emergent space-time, is slowly but surely painting a more coherent, albeit still abstract, picture. We are developing new mathematical tools, new conceptual frameworks to grapple with realities that defy our everyday experience. And perhaps, just perhaps, entirely new paradigms, concepts we haven't even begun to imagine, await us in the coming decades. The universe holds secrets we haven't even learned how to ask questions about. But the human spirit, that insatiable curiosity, that urge to understand, will continue to push the boundaries. We will continue to build bigger telescopes, design more sensitive detectors, formulate bolder theories, and challenge our own assumptions. Because the journey itself is the reward. The pursuit of knowledge, the shared wonder, the collective effort to unravel the cosmos's deepest enigmas, that is the essence of dreamy science. So, as we conclude this chapter, remember this. Nothing is not empty. It is pregnant with possibility. The universe is not static. It is a dynamic, self-organizing symphony of information and energy. And our understanding of it is an ongoing, thrilling adventure. Thank you for joining us on this incredible journey, and we can't wait to explore the next frontier with you. Keep dreaming, keep questioning, and keep looking up.